Carmem is from CBTF, and she will be our lecturer for the morning. Carmem, please.
Thank you.
Can you hear me? Yeah? All right. Thank you very much, Marcelo. Thank you to the organization for inviting me. I feel like I'm at Woodstock and stumbled up on the stage, so I'm very happy to be here and tell you a little bit about the systems that I'm working on. I'm very much an experimentalist in the lab most of the time, so we'll take a break from a lot of equations. You're welcome, AI. So I'm in the lab most of the time. So what I'll tell you about in the next 3 days, today, tomorrow, and on Saturday, is how these systems that we're working with, these are solid-state spin-photon interfaces, how they can be useful for certain protocols, and what kind of things we need to be wary about in the lab when we're working with them. I'll do this mostly based on experimental demonstrations. These are not mine, right? So I'll be presenting work done by people who are much more competent than I am, and that are really sort of seminal to the field based on one particular system. If you want to hear about what I'm doing personally, then I'll tell you about that next week at the workshop. Okay. So, just to introduce myself a little bit, I've returned to Brazil recently. Before that, I was in the Netherlands for a number of years doing a master's in nanosciences, so not specifically physics, but kind of a big lump of different fields. I then did my PhD in Groningen, and I'll tell you a little bit about what I was working with there. And I've been for the past 2 years until last year in Cambridge, right? And throughout this time, what I've been looking at is mostly light-matter interaction. Some people like to classify what I do these days as quantum optics. I like to say that when I'm doing quantum, it's not really on the optics side, and when I'm doing optics, it's very rarely quantum. So it's a combination of the two, but in a different context, and I hope you understand in the next few days. So in my master's, I was looking at different problems, so I've looked a little bit at how iridescence arises in feathers of birds, and that's related to the organization of certain structures in their feathers that diffract light and give rise to this iridescence. And I was looking at how organized these structures have to be, right? So how economic can biology be when actually putting these structures together in order to give rise to the iridescence that is necessary for that has come about in their evolution. I've also looked a little bit at quantum chemistry and sort of simulating electronic states of different molecules that have spin and how these are modified by different solvents, so how these systems interact with sort of disordered environment. Right. And then I've also looked at devices that we fabricate through nanofabrication steps based on graphene, and how we could use these devices to actually detect spin polarization in the electron holes that are pairs that are created when these macromolecules here absorb light in the process of photosynthesis, right? So it's kind of a little bit of different things that I've been looking at. In my PhD, that's really where I started to work with quantum systems, and I was looking at these defects in silicon carbide. So silicon carbide, it's a semiconductor. It's kind of halfway between diamond and silicon. It's a good semiconductor. You can nanofabricate in it, but it's a very hard material, and it hosts a myriad of different defects. Some of these defects interact with light that are in the telecommunication bands. So I was working in the context of a big European consortium composed of different institutions all throughout Europe. So we had collaborators in Sweden who were fabricating these materials. We had friends in Budapest who were doing DFT calculations for us. We were working with industrial partners on sort of the fiber communication side of things. But we were collectively looking at how can we use the degrees of freedom of these systems in order to perform quantum communication, right, to establish quantum repeaters. And I'll go through the ideas behind that, but not really looking at the system a little bit more in the next few days. Right. And then as I moved to Cambridge, I started to look at 2D materials and combinations of 2D materials. So again, these are nanofabricated devices that combine different 2D materials together. And in these type of systems, I was looking at excitonic processes, right? So how do excitons that are created in these systems behave? But I was looking also at defects in layered materials for quantum sensing applications. So thinking really, what are the requirements for quantum sensors, and do these systems fulfill these requirements? Right. Now, since February this year, I've moved, like Marcelo said, I've moved to CBPF. This, for those of you that don't know, it's a research institute in Brazil. It's under the umbrella of the Ministry of Science and Technologies. It's situated in Rio de Janeiro, in a very beautiful spot over here. And there, what I'm trying to do is combining sort of this experience that I've gained to look at these quantum emitters or spin photon interfaces in these 2D materials and how they interact with different degrees of freedom. So for instance, how do they interact with magnetizations of materials that you can integrate them with? And also looking at sort of more traditional spin photon interfaces. These are the systems that I'll mostly focus on for the next few days, and how we can use them as quantum sensors, right? So this is a brief introduction about me, but I also asked you things about you, so you've all received a form that I sent a few days ago. And I wanted to have an idea of who I would be talking to. And what I found out is that most of you are working with theory, right? A lot of you have background in sort of hardcore physics and mathematics. So I figured I'd better not put a lot of equations in this talk, in these lectures, because you're probably much better at them than me. So I'll keep this very conceptual, right? So very, very much, what do we need to look for when we're working with these systems in reality? And I hope to introduce some concepts to you. What I also found out is, I asked you if you had heard about the NV-centered diamond, which is a very prototypical system that we work with. And most of you said you hadn't heard about them. A whole bunch of you said you'd heard about them, but you don't really know what they are, right? So I'll try to keep these lectures kind of from the bottom up. We'll look at their electronic structure today in order to try to figure out what kind of degrees of freedom we have access to when we're working with these systems, right? So what these lectures are meant to do is they're meant to teach you, or to give you an idea of what type of lab jargon we use, right, when we're talking about these systems. What are the strategies that we use to implement some traditional quantum protocols that you perhaps work with on a more quantum information aspect, right? So on a more abstract and universal language. When we have to implement these things in the lab, we need to translate that language to operations that we can actually perform, and how we perform these operations. And that's what I will try to sort of bring to you, is this translation, right, from the quantum information formalism, which is very universal, to sort of the hardware language that we need to use, right? And what are the challenges when we're doing that, right? So in this course, what I'll tell you about is really what are spin photon interfaces and why we need them. I'll show you some experimental demonstrations, like I said, mostly not performed by me, and they're largely based on the NV-centering diamond. And the reason why I choose the system to illustrate these concepts to you is because it's really a prototypical system with a lot of different degrees of freedom that we have access to. And it's useful for all three different types of second generation quantum technologies, right? So we can use the same system, sort of taking advantage of different degrees of freedom that are available for quantum computing, for quantum communication, and for quantum sensing, right? So we can start from the same microscopic description of things and then sort of branch out towards each of the applications that we want to perform. I want to highlight here that it's definitely not the best system for each of these quantum applications, right? There are better systems out there for specific ones. It's just a system that enables you to go any one of three ways, right? So it's useful in that way because you can think about what are the requirements for each of the applications, and you can sort of pick out where these emerge for this NV-centric environment. And then in the last class, I'll tell you a little bit about implementations of quantum communication protocols, both with the NV center, but also more modern ones that take advantages of different degrees of freedom of light and of different defects in materials. And then the questions that I would like you to think about as we go through these examples is what makes a good platform for implementing each of these technologies, right? So what are the emerging properties of the NV that we're taking advantage of, and what are really the outstanding experimental challenges that we're still dealing with, right? So today, like I said, I'll tell you a little bit why we need these spin-photon interfaces, and give you a few examples of implementations of them. And then I'll tell you a little bit about the electronic structure of the NV-centric diamond. Right. Tomorrow, we'll go through some examples of spin control protocols and how they're used to implement quantum sensing and also quantum computing using this platform. Right. And on Saturday, like I said, we'll go through some quantum communication demonstrations, both with the NV and some alternative systems. So you know this much better than I do, but the second generation quantum technologies, quantum computing, quantum communication, quantum sensing, are all technologies that try to take advantages of the quantum mechanical resources that we have at hand, and these are really superposition and entanglement, right? So the goal is to use these properties in a material system in order to implement these technologies. And if we think about what kind of platforms are being considered, we have for quantum computing, of course, we have superconducting devices like the ones that IBM is developing. We have quantum dots, trapped atoms and ions, which Christian has introduced very beautifully, nuclear spin protocols and photonic protocols, and yet a myriad of different platforms that you could take advantage of. For quantum communication, largely we want to use photons, right? If we're communicating, if we're sending information from point A to point B, we typically do that based on photons. But then beyond photons, we need supporting systems, and these are largely based on either quantum dots in 3-5 semiconductors. I'll tell you a little bit about them today. And systems, again, like trapped atoms or ions, which have optical interfaces, Rydberg atoms, which are sort of a cousin, closely related cousin to these. And then if we're doing quantum sensing, we can think about doing that with, for instance, vapor cells of atomic vapors, again, trapped atoms or ions, superconducting platforms, and then defects in solids. These are the ones that I'll tell you more throughout the week. All of these technologies, what they do is they're based on some system that has a quantized degree of freedom, that is isolated from interactions with the environment, and where you can perform quantum control, right? So these are the ingredients that you need. All of these technologies, they will require some type of quantum memory that you can access optically. Right? And what do I mean by that? So these are systems where I can entangle a local degree of freedom, that can be spin, charge, orbital, what you can think of, with the degree of freedom of a single photon, right? And that, the degree of freedom of the single photon that we're talking about can be time-bent polarization, etc. Right? So it's a system that I can draw conceptually like this, right? Where if the system is in a spin up, it interacts with photons of a certain type. If it's in the spin down, it interacts with photons of a different type. And what happens then is that the photons that this system emits depend on the state of the local qubit, depends on the state of this local degree of freedom. And the state of the qubit depends on the degree of freedom of the photon that is absorbed, right? And how come that's useful for the different technologies? Well, for instance, if you think of your quantum processor of choice, regardless of the platform where it's being implemented, one of the requirements we have is that we can create entanglement between any two qubits in that quantum processor, right? And we can choose different forms of doing that. So we can either bring these two qubits together and let them interact for a certain amount of time, right, and create entanglement through this interaction. Or we can create a link between these two qubits. That can be, for instance, a superconducting waveguide for microwave photons and so on. But if I now have two processors that are separated and I want to use sort of the full computing power of these two processors, I need to start thinking of ways of creating entanglement between qubits that are here and qubits that are there, and that starts to become difficult. Right? I can't bring these things in proximity, and a microwave waveguide, for instance, has too many losses to actually make this link. So one option I can think of is to have qubits in these two things that interact with light, and now I can take the photons that these qubits emit. I know that they're entangled with the quantum degrees of freedoms of the qubit, and I can, through a measurement, for instance, project entanglement between these qubits and the photons onto entanglement between the qubits themselves, right? So I can extend this entanglement by performing a measurement on the photons that they emit. Now, what are the requirements in sort of very hand-wavy terms for what I need when I'm doing that? So the first of all is that the photonic interface is very efficient, right? So that the system emits photons on demand. So every time I ask for a photon, I get a photon. And the next requirement is that the spin coherence time of these qubits that are entangled with photons is large enough to perform multiple gate operations, right? So I can use this photonic communication to actually communicate between the qubits, and then I can project that onto entanglement with different qubits inside of the processor. And that's going to become a little bit more concrete tomorrow when we talk about quantum communication protocols using the NV center. Now, of course, for quantum communication, having this link between a solid state qubit or a local memory and a photonic qubit is very important. These are slides that I've stolen from a colleague. I thought they were too pretty to remake. But when we're thinking about quantum communication, we can think of different protocols, right, that we use. In the simplest protocols with the BB84, what happens is that Alice creates a quantum state. She has control over this quantum state, and she sends the entire quantum state to Bob, and then Bob can perform measurements on the state and communicate back to Alice, right? Now, this is a good enough protocol, but it's not the most secure, and it's definitely not the most efficient protocol. So subsequent protocols rely on establishing entanglement between Alice and Bob, right? So now Alice doesn't create a quantum state and send the entire state to Bob, but now Alice and Bob actually have a collective quantum state, right, where they can perform independent measurements on, right? Now, again, one of the problems with this is that when we're actually creating these quantum communication links, we're relying on optical fibers, and when we're sending photons throughout these fibers, we have losses that we need to live with, right? And because of the non-cloning theorem, we can actually amplify this quantum state, right? So, what's the solution to that? The solution to that is to actually extend our network by implementing intermediary links, right? This is what we call a quantum repeater network, and now if we were to establish entanglement between A and H, instead of doing that in one go and living with the losses of very long optical fiber, what we can do is we can break down this communication link, right? And perform intermediary measurements. So this BM here is a Bell measurement. We can perform intermediary measurements in sort of nodes along this network, right? And through these intermediary measurements, we can extend the entanglement, right? So now we have, for instance, a source of entangled photon pairs here in the middle. This source sends one photon to node C, one photon to node D, and now, and we have a different entangled photon pair source here. And this source sends photons to node B and to node A. And by performing a Bell measurement here at the middle, we can then project the entanglement between this and this photon, and that photon, onto entanglement between this photon and that photon, right? So node D and node A now receive photons that are entangled, but they've been entangled through a measurement step over here, right? And we can do that repeatedly, right? And then sort of extend this distribution of an entangled state to A and H. How do we actually do that in the lab? This, when we're talking about photons, this Bell measurement step over here is typically interference on a beam splitter. We've talked about that type of measurements before in the week here, right? So we take these two photons, we make them interfere onto this beam splitters, and then we make a choice over what basis we measure on, right? And this measurement step actually project this entanglement onto these two photons, right? Now, what's the challenge with that? You can think about it. These photons are typically traveling through optical fibers. In order for them to interfere here at this beam splitter, I need them to, first of all, obviously be indistinguishable, right? But I also need them to arrive exactly at the same time, right? And experimentally, that's very, very hard to do, right? Any distortion of my fiber, any change of temperature will slightly change the time at which my photons arrive, and it will degrade this process over here. So what's the alternative? Well, instead of measuring directly on the photons here, I can actually have my photons interact with a third system, in this case, a spin, right? And then I can perform my measurements on this spin. And this interaction with the third system, it doesn't have to be synchronized anymore, right? So if I have my photons traveling through an optical fiber over here, and my photon 2 arrives before my photon 3, what will happen is that the photon 2 interacts with the spin, it changes the state of this spin that I have prepared, right? Now, after this interaction happens, photon 3 can arrive, and it will again interact with the spin, and change its state. And the final state of the spin actually now depends on the states of photons 2 and 3, right? So this quantum state of the spin now carries information about the quantum properties of photons 2 and 3. And now I can perform a Bell measurement on the spin instead of performing a Bell measurement directly on the photons, right? So that's how this type of system can be useful for these type of implementations. What are the requirements in this case? Well, of course, again, the interface needs to be very efficient. I need to guarantee that every time my photon arrives, it will interact with the spin. And the coherence time of the spin now must be large enough to sustain the coherent state until the arrival of the next photon, right? Typically, if we're thinking about 10 kilometers of fiber, for instance, that gives me a requirement of about 30 microseconds or so for the coherence time of the spin. So that's the type of time scales that we're talking about here, right? And that scales, if you make the fibers longer, you need systems that are more coherent. And then finally, for quantum sensing, what we do, and this is again very, very conceptual, what we do is if we have a quantum state that is well described, right, so we know exactly what H0 is and what its effect on our quantum state, we can then use the time evolution of our quantum state to gain information about any type of perturbation that is in the environment, right? Now, this quantum state can either be a coherent state or an entangled state, and you gain certain functionality depending on what case you're talking about. And what's important to note is that you're able to sense both DC, so continuous, and AC fields. Right? Now, for these type of implementations, what do we need? Well, first of all, we need a sensor where we can perform some type of non-invasive reading, right? Readout. And when I'm talking about non-invasive, I mean my target, so whatever it is that I'm trying to sense, cannot be influenced by my readout method, right? So this readout cannot cause any type of heating, depending on what you're trying to sense, or it can interact strongly with what I'm using for readout. My sensor typically needs to be versatile, right? So I need to be able to initialize it well in different situations, and it needs to function in different environments. So typically, if it's a room temperature sensor, it's more versatile than something that only functions when you cool it down to cryogenic temperatures. Of course, the sensor must be sensitive to whatever stimulus you're trying to sense, right? That's a given. And the coherence time of this sensor must be large enough so that I can acquire phase due to very small stimuli. So the smaller the stimulus I'm trying to sense, the more coherent my sensor needs to be. And this, again, tomorrow when I discuss sensing protocols, this will become a little bit more concrete, right? So what are the systems that are being investigated so far? Now, these are systems where I'm not an expert in any of them, so I'll present to you a little bit of the context of where the field is at, right? What kind of strategies people are using on different sensors. But we are looking specifically into solid-state systems. So Christian, I stole a little snippet of his talk yesterday. He said that if you want to trap ions for an actual quantum optician, what you need is a trap, a vacuum chamber, atoms, ionization method, observation method, and then you need these chambers with sort of the ovens that you need to get the vapors and so on and so forth, right? Of course, if you're sort of the most, I could say prototypical is probably the word I want to use, spin photon interface we have is very clearly an ion or an atom, right? That's sort of, you study that in your atomic physics course. It has quantized energy levels. Oftentimes, these energy levels involve some type of spin, and it has optical transitions that you can access. It has all of these requirements. But if you want to work with them, you need this type of platform or infrastructure over here. If you're a condensed matter scientist like I am, and I want to work with ions or traps, what I do is I put them inside a crystal, right? And once they're inside a crystal, they're fixed. I don't have to worry about keeping them in place anymore, right? So I can get away with not having all of these things. What a condensed matter scientist won't tell you is that you then need to worry that the Fermi level of your crystal is correct, that you can couple light in and out of your crystal, that your system is relatively well isolated from crystalline degrees of freedom, and so on and so forth, right? So that's all to say that each of these implementations has its own advantages and challenges associated with it, right? But that's sort of what we're trying to do, is we're trying to take things that work as atoms or ions, and we're trying to put them inside a crystal so that they're easier to integrate with electronic devices, right? So that they're easier to put into a chip, and so on and so forth, right? And what kind of systems are then amenable to that? Well, I would say that the most widely studied so far are probably quantum dots in 3-5 semiconductors. So these are semiconductors like gallium arsenide, indium gallium arsenide, and so on, right? So they're made up of atoms from 3rd and 5th family in the periodic table. And in these quantum dots, what happens is that you start out from the band structure of your of the semiconductor, right? So you have a conduction band and a valence band, and then you create in some way an island over here where the potential changes a little bit. So oftentimes that's an island of indium gallium arsenide, for instance, inside of a gallium arsenide host, right? So the band gap for indium gallium arsenide is smaller than the band gap of gallium arsenide. So you create these potential wells over here that have quantized states, right? So you can think of these as 0D potential wells, right? So you have quantized states for both electrons and holes, and because these systems inherit the properties of their semiconductor host, so these are materials where you have very strong spin-orbit coupling, for instance, so you have already a very strong interplay between optical transitions and spins in these materials. Because these quantum dots inherit these properties, you have very well-defined selection rules for optical transitions in these systems, right? So spins of a certain type interact with a certain type of light, where spins of a different type interact with a different type of light. Now, these things look a little bit like this. So their electronic state is actually very, very large, right? It's about the size of this potential well, which is in the order of 10 nanometers or so, right? Depending on the dot that you're working with. So the electronic state is interacting at the same time with a lot of sort of atomic size of the material. And that has important consequences, which I'll mention just in a couple of minutes. Now, these systems are excellent sources of single photons. So in fact, you can actually, these days, if you have quite a bit of money, you can buy quantum dots commercially that function as very good sources of single photons. Not only that, they're very good sources of entangled photons as well, right? So this is not too recent, but very influential result, where you can create optical transitions in the systems, and you can create biexcitants, right? So these are now combinations of two excitants within these wells, right? And when these biexcitants relax back, they emit photon pairs that are entangled, right? And if you interfere these photon pairs, you can see that the coincidence counts that you get are very low, and what that means is that the entangled photons are relatively good. So these are very good sources of single photons, but they're also very good sources of entangled photon pairs, right? So optically, these systems are, I would say in the solid state, they are unrivaled, right? But because the electronic state is so extended, and because these materials are composed of nuclei that are, or elements that are coming from the third and fifth family of the periodic table, you have some serious restrictions on the behavior of the spin of the systems. Now, if we look at elements that are coming from these two families of the periodic table, they don't have any naturally abundant isotope that has nuclear spin 0. Right? So every single nucleus that this electronic state is talking to, and it talks very strongly to a lot of different nuclei because it's so extended, every single nucleus has a nuclear spin of its own. And what that gives rise to is to a very noisy magnetic environment for these spins. Right? They're at the same time, they're interacting with a sea of tens of thousands nuclear spins. Right? And these nuclear spins are evolving and doing their own thing. So what happens is that they give rise to very fast decoherence for this electronic spin. Right? So these are demonstrations where you use a series of optical pulses to either initialize the electronic spin or perform gate operations, right, on these electron spin. Initialize the electron spin and perform gate operations on these electron spins. And when you do that, you can see oscillations that are what we call Ramsey oscillations, right? We can track the loss of coherence in these systems, and you can see that the coherence time of these electron spins are on the order of 2 nanoseconds. Now, Christian has already told you yesterday, these are timescales that are hard to work with in the lab, right? Let alone if you want to perform operations on these electron spins and sort of control them in some intelligible way. You have to do that before this coherence dies out. These timescales are not very forgiving, right? You can be a little bit smarter, so you can add refocusing pulses here in the middle. So these are the same experiments with the difference that you have a refocusing pulse here. And this pulse, what it does is it flips the quantum state and it allows you to correct for some of the phase that has been acquired during this evolution time. And you can extend this coherence time to about 3 microseconds. So you gain a few orders of magnitude when you're doing that, but these are still relatively short time scales compared to the seconds that Christian mentioned yesterday, right? So what's the strategies that people have been using when working with these systems? Well, there's a series of, and I won't go into detail here, but just to present to you, there's a series of optical control protocols, right, designed to cool down this nuclear spin ensemble that these electron spins are interacting with, right? So I can use combinations of 2 optical pulses with detunings that match the hyperfine splitting between the levels of the electronic spin here. And I can perform cooling cycles where I now sort of transfer angular momentum from the electron spin to the nuclear spin bath, and I can do that repeatedly, right? And when I do that, if I track the time of my sort of Rabi pulse over here versus the detuning, you can see the central frequency over here. That's transitions where no momentum has been transferred to the nuclear spins, but you can also see sidebands, right? And these are transitions where I've pumped my system in such a way that I've removed or added one quanta of nuclear angular momentum, right, to this system. And people can go further and they can extend these protocols, and here I won't explain in a lot of detail. We'll go into these protocols tomorrow, but I won't go into detail over this. But they can extend these protocols and now actually see coherent oscillations of the nuclear spin bath, right? So you can, if you have very good control of your system, you can actually use the nuclear spin bath as a register. So you can store your information in the nuclear spin bath. That takes longer to decohere than the electron spin, so you can sort of do this stepwise transfer of quantum information. So you can use the electron spin of the quantum dot to talk to photons, and use that to control the nuclear spin bath. And then you can use the quantum behavior of your nuclear spin bath as your quantum register, right? Now, on the other side of things, so these are what people for a long time have called artificial atoms, right? They're sort of these extended entities. On the other side of things, people have been, and it's gained a lot of traction in the last couple of years, people have been looking at rare earth impurities in crystals, right? And why people look at these systems, so rare earth impurities are impurities coming from these type of atoms over here, right, from the rare earths. These atoms have valence in their F shell, right? And the F shell is somewhat protected from interacting with the environment because there's some sort of nuclear physics behavior that traps the F shells inside of the D shell. Right? So if I have my valency in the 4F shell, the D shell is actually more spatially extended, and it shields the F shell from interacting with the environment. So if I take a 4F impurity and I place it in a number of different oxides, they will behave largely the same. So if you're talking about an atom trapped in a crystal, I think the most fiducious example of that are these systems, because their atomic properties are largely preserved when you put them inside crystals. They don't really know that the crystal is there, right? So you can then play all of the tricks that Kristen has already mentioned yesterday, right? So you can drive optical transition. This is a result on praseodymium, for instance, a single ion. So you can drive optical transitions, and you have access to hyperfine transitions at times. And depending on how clean your system is, you can even see evidence of these hyperfine transitions in optical spectroscopy, right? So this is a central transition that doesn't involve a nuclear spin flip. And then you have these sidebands in the absorption spectrum of this ion, and each of these sidebands is related to transitions to a different nuclear spin sublevel, right, of a different hyperfine level of the excited state. So these are very coherent systems. Their quantized, their qubit states are very much protected from the crystalline environment. But then you suffer from the difficulties that Kristen has already mentioned yesterday. Their optical transitions are not very strong. You're talking about F to D transitions. The optical transitions are not very strong. You can extend the fluorescence, so you can enhance the fluorescence of this system by putting them into optical cavities, but still, you can't really extract a lot of photons per second from these systems, right? So their optical transitions are relatively weak. So then we look at some type of system that is sort of lying at the intermediary between these, right? So these were earth impurities. They're very atomic-like systems that you put into crystals, and you inherit the advantages of atomic-like systems, but you also inherit the disadvantages, right? The slow optical transitions. And then you have quantum dots, which are great optically, but have these very strongly interacting spin. And then we start to talk about defects in solids. So these are sort of more chemically engineered entities. Some people call them artificial atoms. I like to call them artificial molecules in solids. You really have sort of a more molecular degree of freedom that you can play with. And that allows you to do a lot of different things. Right? So when we're talking about crystals, right, insulators and semiconductors, for example, diamond, these systems often, sort of from the optical point of view, are not the most exciting systems out there, right? They have a large band gap. Nothing really happens optically within this large band gap until you start to create defects in this lattice, right? And when you create defects in this lattice, what can happen is you can create localized electronic states around these defects that live within the band gap of this material. And if you're lucky enough, you can also have access to these optical degrees of freedom, right? And the NV system, I think, is the most prototypical system of this kind. So that's the system that, in the remainder of today and the next two lectures, I'll focus on, right? Why is it the most prototypical system? So the NV stands for nitrogen vacancy. So it's a defect that is, if you think about it, it's really molecular in type, right? It's composed of this nitrogen impurity here that substitutes a carbon in the diamond lattice next to a vacancy, right? And today we'll look at what gives rise to the electronic structure of this defect, right? Tomorrow we'll look at how you can actually use this electronic structure to do cool quantum things. The reason why it's so prototypical is because, of course, the electronic spin that lives inside of this defect can interact or absorbs and emits photons, and that comes from its electronic structure. And it can also interact with various different degrees of freedom, right? So it interacts very strongly with, or relatively strongly with, nuclear spins. It senses electromagnetic fields. That's what you use to actually perform spin control in these systems. And because it's sitting in this crystalline lattice, it's also sensitive to things like temperature, pressure, so on and so forth. So you can think of this as a nightmare. It's a system that interacts with everything. But if you actually gain control over these interactions, then you can use each of these interactions as resources, right, in your protocols. Okay. So today let's try to understand a little bit where this electronic structure of the NV comes from, where these different types of interactions come from. So if we have diamond, it's a relatively simple crystal to work with, right? Despite its many special properties, but it's just carbons that are each bonded to 4 different carbons, and they make these sp3 type of bonds, right? So you have these orbitals that are configured in this tetrahedral coordination over here, and each carbon has its orbitals completely filled, right? Because of it has 4 valence electrons, it makes 4 bonds, each orbital is completely filled, so the valence band arises from fully filled, right? sp3 is just got misconfigured, but the valence band comes from fully filled sp3 orbitals. The conduction band comes from the 3s orbitals of the carbons. Right. This difference in shell from valence to conduction band is exactly what gives rise to this very large band gap that you have for diamond. Now, what happens when you put an NV center inside of this crystalline structure? Now, carbon has 6 electrons, nitrogen has 7, right? So it has 1 extra electron. But because you also have this vacancy here, you end up with these 4 dangling bonds, right? So you have 1 dangling bond from each carbon, plus the dangling bond of the nitrogen, right? Now, nitrogen, like I said, has an extra electron compared to carbon, so it just keeps its electron very close by. You just have this dangling bond for nitrogen that is fully filled, right? And now all the sort of interesting part of our electronic structure will come from electrons that are filling these carbon orbitals over here, right? When we look at the symmetry, right, so you have this nitrogen orbital that is fully filled, and then 3 equivalent, symmetrically equivalent carbon orbitals, which each wants to have 1 electron. Right? Now, if you look at the symmetry of this system, actually these 3 carbon orbitals give rise to 1 fully symmetric orbital and 2 degenerate orbital states over here. Right? And because the system wants to minimize its energy, it ends up in this configuration. Right? So 1 electron is transferred to this fully symmetric orbital, you end up with 1 unpaired electron spin sitting here in these 2 degenerate orbitals. Now that's the configuration for NV0. So the neutral nitrogen vacancy center, which is not the most interesting one. It's not the one that we'll use for a lot of the implementations, and I'll tell you why. It looks like this. It's electronic configuration, right? So it's a spin half defect where you have 1 spin sitting in these doubly degenerate orbitals. Well, the most interesting NV center is actually the negatively charged NV. So you have an abundance of negative charges in your diamond. This defect actually traps an electron and it becomes ionized, only it's now negatively ionized, right? Once it does that, what happens is that you end up with 1 electron in each of these doubly degenerate orbitals. And because of sort of just high school filling of orbitals that we've all learned, because of Hund's rule, these 2 electrons end up paired parallel to each other. Right? So the NV negative, the negatively charged NV center, is now a spin 1 defect. So it has a spin 1 in the ground state. It's not a singlet, it's not a spin half system, it's a spin 1 system in the ground state. Right? I can also have different configurations to this. So I can, for instance, come in with light and I can excite 1 electron from this orbital to that orbital and create an optically excited state. Now, again, this optically excited state is also a spin 1, right? I still have in this system 2 unpaired electron spins, and they're pointing parallel to each other. So the optically excited state of my spin 1 manifold looks like this. Now, you can think, well, I could also have different configurations where I have the 2 electron spins now pointing anti-parallel in a singlet configuration, right? And that actually gives rise to a singlet manifold that is quite useful, in the optical cycle of this defect. And I'll tell you a little bit in the next few minutes. Right. So now optically, the electronic structure of this system looks like this, right? So I have optical transitions here. These optical transitions are around 637 nanometers. So my system absorbs light and emits light at this wavelength. That's this peak that you see here in these optical spectra. So here I have a arbitrary signal versus wavelength for both an absorption experiment and a photoluminescence experiment, right? So the black curve over here is light that my system absorbs, and the red curve is light that my system emits, right? So photons that the NV emits versus wavelength. And optical transitions here between my two, my ground and my optically excited state give rise to this little peak over here. Now, if I look into detail in this peak, and this is not something I'll mention today, but it will be important on Sunday, you actually have selection rules that are spin dependent in these systems, right? So because of the symmetries of each of my spin states, I can actually select optical transitions based on polarization of light, and that's something that we'll use in entanglement distribution protocols for these defects, right? Now, I had removed this guy, but okay. Forget about this guy. Now, my defect, like I said, it lives in the lattice, right? So it also interacts with vibrational degrees of freedom of the lattice, and that's where I need to start thinking about what's the impact of the crystalline environment on what I can do with this system, right? So I not only have these direct optical transitions from ground to optically excited state, but I can also drive transitions that couple to photons in the lattice, right? So each of my ground and excited state live in its own sort of second harmonic vibrational potential, right? And it can couple to photons, right? In a way that I can also drive transitions that are more energetic, where I drive transitions from my ground state to a vibrationally coupled right excited state. And that's what we see here as this sideband, right? On the sort of higher energy side of the absorption spectrum. Right? In the same way, when the system is decaying from the optically excited state, it can decay to vibrationally coupled states over here, and that gives rise to that sideband, right? The sideband of emission. So that's where, and I wish this wasn't here because it's a bit distracting, but that's where the first limitation of the NV center starts to really appear, is if I'm talking about doing quantum communication or photon-dependent implementations based on this system, I'm talking about using coherent photons, so photons that I can reproducibly get to interact with it. So I either want to get photons that I know will come at that wavelength, or I want to use a certain particular wavelength of light to interact with the NV. And what you can see from here is that these optical transitions from the NV that are coupled to these coherent photons are just a slight part of the total optical transitions of the system, right? So the system is very bright. It typically emits on the order of a megahertz of photons, right? So megacounts per second. But most of its emission is photons that are useless for quantum communication protocols, right? If I want to do quantum communication protocols, I want only the photons that are emitted here, and that's sort of a tiny percentage of the total number of photons that my system emits. So that's one of the motivations for looking at alternative systems, and on Sunday I'll mention that a little bit more. Now we've talked about the optical manifold, right? So the optical degree of freedom. Now what about the spin degree of freedom? I told you that the ground state of the system is a spin 1, right? So spin 1 has 3 different spin sublevels. My spins can be either paired down, or in this triplet ms equals 0 state. And in a system that is spherically symmetric, these sublevels must be degenerate, right, if I don't apply any magnetic field. Now, this system is not spherically symmetric. You can look at its sort of structure over here. And I told you that my electronic state is sitting on these 3 carbon orbitals over here. So it's kind of sitting in a donut or pancake-like type of configurations. And that means that spherical symmetry is broken, and that I can actually have broken degeneracies between these sublevels, even at 0 magnetic field. Right? And you can understand that if you think about the dipolar fields that each of the spins create, right? And that this dipolar interaction actually depends on whether my spins are parallel or anti-parallel, because these spins are sort of locked to this pancake or donut-like configuration, right? So you can think if my first spin is up, it creates a dipolar field like this, right? My second spin will feel this dipolar field, and depending on whether it's pointing down or it's pointing up, the energy of this configuration will change, right? It's either aligned parallel to the dipolar field of the first one, or it's aligned anti-parallel to the dipolar field of the first one. So what that gives rise to is to this zero field splitting over here. That's what we call this zero field splitting, which in this case is about 2.8 gigahertz, right? And that already breaks some of the spin degeneracy of the system, even in the absence of any magnetic field. Right? Now, it's useful, I think, to remember that this splitting, this energetic difference for the 2 spin configurations, it arises from magnetic dipole interactions between the 2 spins, depending on the distribution of my electronic state. So if I change the distribution of my electronic state by, for instance, heating up the diamond and changing the lattice parameter of the crystal, I'm also going to change the size of this interaction over here, right? So there's an energetic signature on my system if I change the distribution of the electronic state, right? Now, the last interaction that I want to bring is I can, of course, apply a magnetic field onto the system that breaks the degeneracy between ms equals +1 and -1 states. So now I have fully non-degenerate spin states that I can isolate and use as a qubit, right? In any way that I would typically do that. And I can then use microwave, so either continuous or pulsed microwaves, to drive transitions for my spin. Right? Now, if I look at the Hamiltonian that describes only the spin of the system, right? So this is the Hamiltonian only when I'm talking about this manifold over here. Right? It's the Hamiltonian that acts on the spin of my system. It's, like I said, it can look like hell. What we have is this zero field term that comes from the dipolar coupling between the spins. We of course have an electronic Zeeman interaction, right? So this is interaction with a magnetic field. We can interact with electric fields because of this change, right, of the electron distribution when you apply electric fields. So I have a term that describes some type of interaction with an electric field. And I of course can interact with different magnetic dipoles from, for instance, nuclear spins, right? So I have a hyperfine interaction term, and then whatever my nuclear spins are interacting with. Now, I've told you about the optics of the system, and I've told you about the spin. How do they come together, right? What's the photodynamics of the system, and how does that present resources that I can use in these quantum protocols that I'll describe tomorrow and on Saturday? I can drive optical transitions between ground and excited state. I've already told you that. And my system can decay via optical relaxation and emission of a photon, but it can also decay non-radiatively, right, via transitions into this singlet manifold, right? So this is where I excite my system. It interacts somehow with the phonon in the lattice, and that creates a spin flip that brings me into this spins into the singlet manifold. Now, what's special for these type of spin-1 systems, and the NV is not the only one of them, but it's for sure the most prominent, is that these non-radiative transitions are spin-dependent. Right? So the likelihood of going through a non-radiative decay pathway is spin-dependent. Right? Whereas the optical transitions that I'm driving, they are spin-conserving. And that gives rise to two important features, right? The first important feature is that I can call one of my spin states bright and the other one dark, right? Because if I'm in this spin state and I'm cycling optically, the chance of me ending up in this sort of non-radiative shelving state here is very small. So I just, if my laser is on, I just keep cycling between these two states. I keep emitting photons, right? Now, if I'm in this state and I turn my laser on, what happens is that the chance of being trapped in this shelving state here is relatively high. Right? So depending on whether I start from this spin state or that spin state, I will emit more or less photons per second. So consequence number one is that the photon emission rate of the NV directly depends on the spin state. So I have a readout mechanism, right, both for resonant and non-resonant excitation that is spin dependent. Yeah. Now, the second consequence, which I think is more important than the first one, is the following. If I'm cycling between ground and excited state through optical excitations, right? I just told you that if I'm in this dark spin state, the chance of ending up in this singlet manifold is higher. Right? Once I end up in the singlet manifold, my system just decays normally, right? So it decays within the singlet manifold and it ends up here. But now the chance of coming back to my triplet ground state is equal. That's no longer spin dependent. There's no spin memory to this process. Right? So what happens is that after a few cycles of illumination, I pump population from this level onto this level, and once I'm here, I have equal chances of ending up in the bright state. Right? So if I illuminate my system for a certain amount of time, what ends up happening is that I polarize my spin. So I can cool down the spin state of my system through non-resonant excitations, right? So that's consequence number two. The NV allows you to initialize the spin, right, through repeated optical transitions. This is very similar to a spin pumping protocol for free atoms, but it's a spin pumping protocol where you can come in with non-resonant light, so you can filter out this light. It doesn't have to be part of your experiment afterwards, right? And this can happen even at room temperature, right, in a crystalline environment, which is not typical. Right? So I can use fully non-resonant protocols to initialize my spin, even at room temperature. So these are the two consequences, right, of the photodynamics of the system, which all arise from this electronic structure that I've discussed today. So today was kind of more of a molecular orbital derivation. Tomorrow we'll look at how we can use these processes, right, in quantum implementation protocols. So what are the parts of these processes that we need? What are the ones that we don't need? And what kind of protocols we can implement, right? But the main message of today is that this is a system where I can establish a very simple qubit operation loop where I can use light to initialize my system, right? I can then use microwaves to manipulate the spin, right? So that's where my quantum happens. And then I can use light again to read out the system in a very natural way in a crystal at room temperature, and so on. So thank you very much today.
Questions?
Thank you for the talk. I have a question. Usually when you have an EV center, you're going to have a single EV center that you're manipulating or multiple. Because I mean, if you have multiple, maybe they can like interfere with each other and then affect the performance or stuff like that. I don't know.
That depends on the goal you have. You can control the concentration of NV centers in crystals relatively well these days. So you can have very dense ensembles, which are often useful for sensing applications, where you want to parallelize these things and sort of cut out on your readout time, right? So you can interrogate a lot of NVs at the same time, and that gives rise to some parallelization of your protocol, but it reduces your spatial resolution, right? So you now are limited by, I'll say this again tomorrow, but you're limited by the spot, right? How tightly you can focus your laser in the crystal. But for both quantum communication and quantum computing protocols, you're always working with single NVs, right? You're working at the limit where your crystal is dilute enough, the concentration of NVs is dilute enough that you can identify single NVs and work with them. They're bright enough, they emit enough photons per second that you can still get away with looking at a single NV.
Thank you for the lecture. Impressively well explained for someone who's not from the area. I really think I got a lot. My question is about how do you select which two levels you want to use as your qubit? It's more of a convenience. For example, if I have a particular kind of laser, I'm going to choose the kind of transitions that allow me to use that frequency. Does it have something to do with the stability, like the time I can maintain it coherently in that level? Or that would be the question.
So if you're talking about communication protocols where you really need sort of this photon entanglement step to happen, then you want to deal with two levels that are symmetrically different, right? Where you have selection rules for transitions. And then you will work with typically these two, right? So MS+1 and MS0 states. They're the ones that are going to give you smaller microwave frequencies to work with, which is typically easier, right? If you're dealing with this transition, then your microwave frequency rapidly goes up and goes beyond the typical microwave setups that we have. And this transition is a delta MS=2, which is technically forbidden. So this is not a good qubit. Right, this is hard to drive. So you would typically look at MS=0 to either plus or minus 1, and for convenience, we usually look at the lowest energy microwave.
Hi, thank you very much for your talk. I have two questions, if that's okay.
Where are you?
The first one about this microwave transition. The coupling between the electromagnetic field and the spin transition, is it the magnetic field, or is there some sort of spin orbit coupling to enhance this transition?
So for this system, it's the magnetic field. So you're coupling to magnetic dipole, just typical ESR experiment. Yeah, spin orbit coupling for the NV it's very small. For other systems, and I'll discuss them on Saturday, spin orbit coupling starts to be more important, right? But yeah, it's a factor to take into account for other systems, but not for this one.
Okay, thank you. And in the last picture. The transition between the spin 1 and spin 0, you said it's non-gradient. So what is the mechanism that this is transition?
This is a process that chemists study a lot. It's called inter-system crossing. And it's an important process, for instance, when designing molecules for solar cell applications and so on, right? It's a bit of a mystery. So actually, I draw this from this excited state. I should not have done that if I were more rigorous. I should have drawn it from one of the vibrational levels. Yeah. So it's when you excite non-resonantly to a vibrational level. Over here, there's some crossing between the vibrational parabolas of the spin 1 and the spin 0 manifolds. And when that crossing happens, you can have some vibrational process that actually changes your spin. And that does depend on spin-orbit coupling, otherwise this process would be forbidden, right? So otherwise that wouldn't happen. So it's faster in other systems where spin-orbit coupling is more prominent. But it's a bit of a mystery. So it's called inter-system crossing, and these systems have been studied now for 25 years, and I think there's no definitive answer to what's the microscopic scattering mechanism, because it's a scattering mechanism, right? What's the microscopic scattering mechanism that actually drives this inter-system crossing pathway? It's something that we try to control, right? Because it gives you a lot of control over how quickly you can initialize the spin, right? So the ratio of this, or the spin selectivity in this process determines how quickly you can initialize the spin. So we've tried, as a community, we've tried different defects and different configurations to try to enhance this inter-system crossing pathway. And there's some ideas of what can do that or not, but we don't fully understand the microscopic scattering mechanism.
Thank you for the talk. Great slide presentation. I think Fernando de Mello has a competitor now, in my opinion. It's a simple question, maybe my lack of knowledge, but in an NV platform, you always work with a single qubit, or you can have a multiple qubit system and interact them, entangle them?
We'll talk more about that tomorrow, but you can use the NV as a central hub and talk to different nuclei, for instance, right? So you can have a multi-qubit platform based on different nuclei. You can also entangle two NVs that are remotely that are remote, right? That are separated. So these implementations have been demonstrated. Now, using one NV to control different nuclei and using another NV to control different nuclei and then entangling them, I think that step hasn't been done. It's an important step to scaling up, right? But you can work with multiple qubits. I don't know if your original question was similar to the previous one, whether you can work with ensembles or no. Okay, so you can work with different NVs and you can entangle them through different types of interactions. Yeah.
I have a question myself.
Yeah.
What is the limitation for the pumping mechanism? Like, what is the purity that it gets for the bright stage in the end?
So if you're doing preparation for quantum computing or communication, you would prepare through these transitions, right? Through a typical optical pumping technique. So not relying on this inter-system crossing. If you're doing anything at room temperature for sensing, for instance, then you rely on this inter-system crossing. And typically, so it depends a little bit on the power. The length scale of spin relaxation, which is typically what limits how well you can prepare, is tens of milliseconds even at room temperature. So it's fairly long compared to this preparation mechanism. You can get pulsed contrasts of nearly 50%. So it's not 99.99999, right, from atomic physics, atomic systems, but you can get preparation of close to above 95% or so.